Alright, so my basic question, like why I was looking at Pascal's triangle and the binomial theorem, etc. The multinomial theorem. Because we forgot that polynomials are a thing and polynomial means multinomial. God damn it. Anyway, why are the following equations describing the same exact thing differently? Okay, so what we got here, and this one I edited like 7 times, so there's an N in front of a consonant. Anyway, that's the way we should write it actually. We'll just do like French and not pronounce the N because it's always the same word and it's always related to the number 1. Anyway, areas of regular n-gons relative to a circumscribing square of area 1. So yeah, I still fucked it up. Anyway, anyone who thinks that I think that I'm always right is fucking not paying attention. N mod 4 is 0, so now the number of sides is a multiple of 4. Okay, so what's happening here is we get this. N mod 4 is 2, so it's even but not a multiple of 4. We get this. Really, the only thing that changes is this 2n in the denominator of the angle in the denominator. N mod 2 is 1, so it's an odd number of sides. We get this. And when we get to a circle, it's this. I reject the notion of a pyragon. That's the name is terrible, and the concept is terrible. No. Just goes to a circle. Fucking Christ. Okay, so notice on a bunch of these, there's a 4. On this one, there's not. And the reason for this, if we put that 4 back in its place where it came from, we can see what's happening. In the denominator here, we have these 2 things added together squared, 2 things added together squared, 2 things added together squared, 2 things added together squared. When they're the same 2 things, we get a 4. When they're different, we don't. But it's actually the same exact thing. So in most of these forms, we get a division by 4 resulting from the squared base 1 binomial in the denominator, but we only get that 4 when both terms of the binomial are identical, because the number 4 only works when it's describing the quantity of a single type of thing. So here, cos pi on n plus cos pi on n quantity squared is quantity 2 cos pi on n squared is 4 cos squared pi on n. Okay, that 4 comes out because these 2 things are the same thing. Quantity 1 plus cos pi on n squared is 1 plus 2 cos pi on n plus 1 cos squared pi on n. So now these coefficients, 1, 2, 1, are the 4. That's what the 4 is now. And we can get that trivially from the binomial theorem. You can just foil the bastard. Like, you can find it in multiple ways. It's definitely there, this 1, 2, 1 thing. And if these are there, you'll get 4, but this is a higher level abstraction. Right? This 4 is a higher level abstraction. You have to recognize that all of the parts are the same thing. Okay? So it's curious that the currently accepted foundation of mathematics treats these so radically different, but they're definitely the same exact thing. This 4 is a 1, 2, 1. It's the same as this. It's not different. The difference is the units on these are not the same. They're not commensurate, right? It's interesting because this is pretty ancient knowledge, but figures like Dedekind and Peano and Whitehead and Russell came in and they're like, oh, we understand how numbers work, and they only used these bastards. This very high level abstraction, and they tried to derive everything from that. It's pretty obvious as soon as you take a look at anything that that's bullshit. Come on now. This thing is the same as this 4. These equations are all describing exactly the same thing in exactly the same way, except that we have this special notation for this concept here that doesn't translate in any way to what's happening here. This is a fault of our notation. This isn't something fundamental about mathematics. This is a mistake that we made when we established our notation and our way of thinking about it. We got numbers wrong. And it's worth noting that there are other ways to create 4, right? It doesn't only come from squaring 2. But that's also important. Those other 4s, the way that they come about, that context is lost when we use this abstraction. When we use this symbol to abstract it, we lose that context. And this is directly related to why division by 0 is undefinable. Because the only times where you can divide by 0 and get something meaningful out of it is when the numerator establishes a context. You have to know what in the hell we're even doing. If it's abstracted to this point and we've thrown the context away, you can't divide by 0 because you don't know what the hell you're doing. So this abstraction comes at a very high price. We lost a lot by doing this. And we've kind of just been staring this in the face throughout the entire history of algebra, at least. And it's older than that. It's significantly older than that, really. But, yeah, this is a fundamental problem. I don't know how to solve this. I don't know how to work around this right now. And I may never. But this is something that should probably get some attention because this is a very basic fucking problem that nobody is worried about. Oh, we know how numbers work. No, you don't. You don't. You kind of know how to get around the fact that you don't know how numbers work. Like, this is definitely well studied and well understood. I'm not saying that I'm coming up with anything new here, right? Don't be an idiot. That's not what I'm saying. What I'm saying is this coefficients 1, 2, 1 is the same thing as this 4. This 4 here is identical to this, but we don't have any way of indicating that. And we should.